Hi everyone, today's topic is exponential functions and graphs. In today's screencast, what I want you to learn is how to graph exponential equations and functions, and we're going to solve a couple applied problems. To get started, let's look at what an exponential function looks like. In an exponential function, your variable is in the exponent. That's essentially what an exponential function is. Now, what I'd like you to do is plug in some values into this function, and let's make a table of those values. So, for example, if we plug in -2, -1, 0, 1, and 2, and those are the numbers we plug in for x, what do we get for y? What are the f of x values? I wanted to point out, in case you forgot your rules for exponents, what does this mean when you're plugging -2 in for x? Well, then you're being asked to raise 2 to the -2 power. Do you remember a negative exponent means you're going to write 1 over 2 to the second power? It's the reciprocal. And 1 over 2 squared is 1/4. Also, remember, anything raised to the 0 power is equal to 1, and that's why 2 to the 0 is equal to 1. Plug that in your calculator and verify that your graph looks like mine. This is the graph of this exponential function, f of x is equal to 2 to the x. And you can think of this as a sort of basic graph. A lot of exponential functions look similar to this. They might be a little stretched vertically, horizontally, or shrunk vertically or horizontally. But this is basically our basic shape. And so I want you to think about some of the characteristics of this graph. What is the domain of this function? What values are we allowed to plug in for x? Well, all real numbers. You can plug any number in for x. You can plug a positive number, a negative number, a fraction. It doesn't matter. So all reals. But this range is not all reals. You should notice that you're going to get a horizontal asymptote. That's the next characteristic. And that horizontal asymptote is when y is equal to 0. It's the x-axis. So the range goes from 0 to infinity. And 0 is not included. And I want you to look at the equation. Go back to this equation and understand why. 2 to the x cannot be equal to 0. Look at these values. You can get really small values, but the smaller you get with your x value, 2 to the -99th power, is still going to be 1 over 2 to the 99th power. So it's really small, but it's not 0. You can't get 0. There's no exponent that you can plug in so that 2 to that power is going to be equal to 0. Okay, let's look at another one. So look at this equation. F of x is equal to 2 to the x plus 3. Think about what you know from your section on transformations and talk about how this graph is going to be different than what we graphed before. What is that plus 3 in the exponent going to do? Well, I've graphed both of these functions on the same screen. So in blue, you have the y equals 2 to the x graph. And in red, you have y is equal to 2 to the x plus 3. Notice this graph is shifted to the left 3. This is like a parenthesis. The exponent is like a parenthesis. And that plus 3 inside is shifting the graph to the left. This is a horizontal shift. And now let's talk about those characteristics. The domain is the same, all reals. The range is the same, 0 to infinity. We have the same issue. 2 to some power is not going to be equal to 0. And the horizontal asymptote is still y equals 0. Okay, look at this next example. What do you think's happening with this graph? Now that plus 3 is not in the exponent, it's on the outside. So how is that going to affect the graph? Hopefully you realize it's shifting it up 3, right? Just like we saw with the transformations, the chapter on transformations. So once again, y equals 2 to the x. You can think of this as our basic function, our parent function, if you will. And then in red is y is equal to 2 to the x plus 3. And the graph is shifted up 3. And the characteristics, the domain, all real numbers. You can plug anything in for x. But the range here goes from 3 to infinity. It will never be equal to 3 because 2 to the x cannot be equal to 0. But it's going to come pretty darn close. So that's our asymptote. Y equals 3 is our asymptote. Making sense, I hope. All right, another example. What about this negative sign? What's this going to do to the graph? Remember, the negative sign is a reflection, and this one is reflected over the x-axis. So, when we have a negative sign outside or in front of this exponential function, then we have a reflection over x. The domain of the function stays the same, all real numbers. But the range of our function is different. The range starts from negative infinity and goes to 0, but will never be equal to 0. And the horizontal asymptote is the same. In this next example, the negative sign is in the exponent. How does that affect our graph? Oh, I forgot to mention, 2 to the negative x, remember by definition means 1 over 2 to the x. So these are going to be the same graph, right? And if you notice, what happens here is we have a reflection over the y-axis. And that makes sense. This all is exactly the same thing that we learned a couple sections or a couple chapters ago when we learned about transformation. See how this is all coming together? So this graph was reflected over the y-axis. What's the domain? All reals. What's the range? 0 to infinity. And what's that horizontal asymptote? Well, it's y equals 0. Okay, so that's all there is about graphing exponential functions. You'll have plenty of examples in your homework, and you can use your calculator also to verify your graphs. So what I want to turn our attention to now is the application of exponential functions. And there's lots and lots and lots of examples of applications of exponential functions. What we're going to focus in is one that has to do with money, because that's pretty pertinent to everybody in the class. So we're going to talk about the compound interest formula. Chances are you have some money in some account that is earning compound interest. And there's a formula for compound interest that looks like this. A is equal to P times 1 plus R over N to the NT power. Let me explain to you what each one of these variables represents. A is your future value. That's the amount you're going to have in the account. That's going to be the principal plus the interest. Your initial investment plus the interest you earn together gives you the future value. P is your present value, or think of it as your initial investment. That's the amount you're putting in the bank. R is the interest rate you're earning, and in this formula, it needs to be written in decimal form. N is the number of compounding periods per year, and T is your time in years. So when we're talking about compounding periods, I just want to make sure this makes sense. So if your money is getting compounded annually, that means once a year. Semi-annually means twice a year. Quarterly means 4 times a year. And monthly means 12 times a year. That's typically what you're going to see when you're talking about compound interest. Sometimes they talk about daily, and typically if they're talking about daily, it would be 360, even though I know there's 365 days in the year. Sometimes they use 360. That's called the banker's rule. But I don't think you do that in your textbook. I looked real quick, and I don't think you do. Okay, so the next screen. So what we're going to do is we're going to apply this formula to a problem. So suppose you have $10,000 that you're going to invest in an account that pays 6.5% interest, which is compounded monthly. How much is in the account in 5 years? Well, for the numbers that are in this formula, P is going to be equal to 10,000. That's our investment. The interest rate was 6.5%, written as a decimal. That's 0.065. N is 12 because it's compounded monthly. So N is going to be 12. And T is our time in years, and it's 5 in this example. So when I plug those into my calculator, and you want to be careful plugging it into your calculator. Those of you with newer calculators, it's not too bad because your screen will look like mine. But if you have an older calculator, I would do 12 times 5 in my head before typing it in my calculator, or put it in parentheses. But in the newer calculator, the screen looks like this. But in any case, the answer is that you have earned $13,000. That's incorrect. You have $13,828.17. You've earned $3,828.17 in interest. But this is the total amount in the account. This is including the principal and the interest. Okay, let's turn our attention to another kind of question. So what if I asked you this question in a different way? Suppose $10,000 is invested in an account that pays 6.5% interest, compounded monthly. How long will it take for the amount to reach $40,000? So I want to pause this for. So I paused the screencast and changed this because I realized I hadn't changed the T from the previous problem. So I want you to notice, and I'm drawing attention to this, that this is the variable we're looking for. How long will it take for the amount to reach $40,000? The variable we're looking for in this problem is T. Our principal is still $10,000. Our R is 0.065. That's the interest rate. It's still compounded monthly, so N is 12. But now we know the amount in the account. The amount in the account, the principal plus the interest, is $40,000. So the equation we need to solve is this one. When does this equal $40,000? Well, at this point in our course, you don't have the skills yet to solve this algebraically. So to solve this problem, we're going to have to do it graphically. So we're going to have to plug this formula in our calculator. So we're going to have to plug that into y. So this will be our y1, and this will be our y2. We're going to graph this. And you're going to have to change your window. So here's the window I changed mine to. See, the X min and the X max. In this problem, oh, by the way, when you're typing it in your calculator, you're going to use an X for T. And so the time is going to be between 0 and 50 years. Okay, and the Y is the amount of money you have. So the least amount of money you have is 10,000. That's what you started with. And it needs to grow to 40,000. So I'm going to make my window 60,000 so that I see everything in the picture. And with those adjustments to the window, this is the picture I see. The blue graph is what we have on the right, and the red graph is what we have on the left, right? This is y equals 40,000. This is y equals 10,000 times 1 plus 0.065 over 12 to the 12x power. Then you're going to use the second calc feature on your calculator and find the point of intersection. And the point of intersection ends up being approximately 21.4 years. That's about 21 years and 5 months. So in 21 years and 5 months, you will have 4 times the amount of money that you invested. Okay, now, this compound interest formula helps us to understand the irrational number e. E is sometimes called the natural number. So I want you to consider this scenario. Suppose you have $1 and you invest it at 100% interest, which is compounded for 1 year. So our formula looks like this. Now, I haven't told you how many times it's compounded. It could be compounded annually. It could be compounded quarterly. It could be compounded semi-annually or monthly or daily, right? And this is all plugged into this formula here, or those values are plugged into this chart here. And it tells you how much money you would have based on these conditions. Now, what I want to show you are the compounding periods. Is I want to show you this number is getting bigger, but you would expect this to get really, really big. If I told you this money was getting compounded per second, you would think, oh my God, I'm going to have a ton of money after a day. But you really aren't. It's starting to slow down. The growth is starting to slow down. It starts growing fast, really a lot fast, but then that growth starts to slow down a bit. And if you were to change those compounding periods to infinity, it's getting compounded an infinite number of times per day. And you plugged infinity into this equation, and you'll learn more about this in calculator, but you're going in calculus, I meant to say, you're going to get closer and closer to this number e. And this number e is an irrational number, kind of like pi. It's one of those kinds of numbers, and it's 2.71828, etc. It does not repeat, even though it looks like that here. It's definitely an irrational number. Now you can pull that number e up on your calculator. There are two keys that have to do with e. Just the number itself, which is what I used here, is above the division sign on your calculator. So you'd press second and division to pull that up. But there's another e on your calculator. It's right here. It's above the ln button. And this is e to the x. I used e to the x in the next set of problems that I gave you. So in the next set of problems, I'm asking you to just practice plugging this into your calculator. Plugging in e to the fourth or plugging in e to the negative 2.345. And hopefully when you plug them in, you get these numbers. You can pause the screencast anytime you want to check to see that you've gotten these answers. And I just want to show you one more time with the calculator that I'm using here the e to the x button so that I can plug 4 in. I can plug negative 2.345 in for my exponents. Okay, I hope that helps. The only thing left to tell you is I want to make sure you practice graphing these on your calculator. So the graph of e to the x minus 1 looks something like this. Just verify that you've got this going on with your calculator and you don't have any problems. Email me with any questions. I'm here to help.